Good morning, everyone. I am K Siva, Assistant Professor of Physics, Krishna Reddy Engineering College. Today we are going to discuss about the topic dielectrics. In this topic, the contents are: what are dielectric materials, parameters of dielectrics such as dipole and dipole moment, electric flux density or displacement vector D, dielectric constant or relative permittivity of the medium epsilon r, polarization and polarizability alpha, dielectric susceptibility chi, and the relation between dPe, D electric displacement vector, and P is polarization vector, E is electric field. So basically, what is a dielectric material? Dielectric materials are electrically non-conducting materials such as glass, ebonite, mica, rubber, wood, and paper. Dielectrics are insulators, as we know that. Then what is the difference between insulators and the dielectric? Why they are categorized as a separate dielectric materials? In insulators, there is no conductivity. When we apply high electric field, there will be no change in the electronic properties. But certain insulators, they exhibit a different phenomena, which is known as polarization. On that basis of polarization, those insulators which exhibit this polarization process, they are known as your dielectric materials. So they are actually they are electrical non-conducting, but there is a little bit chance of electrical conductivity. So the example of dielectric materials are glass, ebonite, mica, rubber, wood, and papers. All dielectric materials are insulating materials, as we know that. All dielectric materials are insulating materials. The difference between the dielectrics and insulators, that is their applications, how we are using. So that is, if you compare the insulating material with the dielectric materials are more applicable. That is, if the main function of is non-conducting material is to provide electrical insulation. So that's why they are your insulators. On the other hand, if the main function of non-conducting material is to store the electrical charges, that means we can store the electrical charges in dielectric materials. So that's why they are called your dielectrics. For example, as we know that mica, glass, water, plastic, and polar molecules. So next, what is the dipole? A system consisting of two equal and opposite charges, that is plus q and minus q. So the magnitude of two charges should be equal, and they should be separated by a small distance. So the system consisting of two equal and opposite charges, that is your plus q and minus q, separated by a distance d, then it is called your electric dipole. Next, what is a dipole moment? Mu, which is denoted by mu. This is a letter mu. The product of magnitude of charge, any one of the charge, either it can be plus q or minus q. The product of magnitude of the charge and the distance between the two charges, d, small d, which is called your dipole moment. And the dipole moment, which can be written as mu is equal to q multiplied by d. So the multiplication between the charge, magnitude of any one of the charge, and the distance between them. And the unit is coulomb meter, because the unit of charge is coulomb and the distance which is measured in meter. So that's why the unit is coulomb meter. So this is a diagram related with your dipole moment. So this is a dipole. This is plus q, this is minus q, and these two charges are separated by a small distance d. Next, what is a permittivity? Permittivity, the definition has its own meaning. Permission to a particular field. So that's why it is your permittivity. Permission to a electric field. That is your permittivity. It is denoted by epsilon. The permittivity represents the dielectric property of a medium. It indicates easily polarizable nature of a material. Its unit is farad per meter. It's very important. In electricity, we know that we are using epsilon naught. Epsilon naught for not for vacuum. If epsilon naught is there, that's for vacuum. If only epsilon is there, That is a particular medium other than the vacuum. It may be it may be a glass, it may be any other medium other than the vacuum. So simply permittivity, how we can define a permittivity? Permittivity is nothing but the permission to a particular field. Next, dielectric constant, which is denoted by epsilon r, which is also known as your dielectric constant. So epsilon r for dielectric, that is relative permittivity. A dielectric characteristic of a material is determined by its dielectric constant. It is a measure of polarization of the dielectric. If the K value, that is if epsilon r value is more, then the polarization is more. If its value is less, then the polarization is less. Next, dielectric constant or relative permittivity. It is defined as the ratio of permittivity of a medium to the permittivity of free space. So epsilon r, as I told that epsilon r is equal to K. Both are same. You should remember this. Very important. Epsilon r is equal to K. So it is the ratio between epsilon to the epsilon naught. So again, it can be defined as the ratio between the C by C naught. C is the capacitance. Here it is written that C naught is the capacitance of the parallel plate capacitor when there is a air medium. So air medium, when it is air medium is there, then its value is C naught. And C is the capacitance of the parallel plate capacitor when a dielectric medium is kept inside the two plates. Okay, so epsilon r, which is known as your relative permittivity, it is also known as dielectric constant. It is the ratio between epsilon to the epsilon naught, which is also defined as the C by C naught. C is the capacitance when a dielectric medium is placed between the parallel plate capacitor, and C naught is the capacitance of the parallel plate capacitor when this air medium is present. Next, electric field. What is electric field? It is the space around a charged body up where its influence is felt. That is, if there is a charge Q is there, if charge Q is there, then there is around the charge Q, there will be some force. So that field, the region surrounded by the charge where its force exists, it's known as your electric field. It is a space around a charged body, whether it can be a positive charge or a negative charge. Next, electric field induction or flux density. Which is known as, that is electric field is also known as your electric field induction or flux density. That is your capital E. The electric field is denoted by E. Next, displacement vector. So it is defined as the number of electric lines of forces received by a unit area. So the equation is D is equal to Q by 4 pi R square. 4 pi R square is the area around the charge. Q by A. Q is the charge and A is the area surrounded by the charge. So area, if it's a spherical shape, then the area is your 4 pi R square. So where is the surface area? But at a point, the electric field intensity is given by, we know that in E is equal to 1 by 4 pi epsilon naught, Q1, Q2 by R. So this is your Coulomb's force. But the definition of electric, as we know that electric field intensity is nothing but the force exerted by the unit positive charge. Since one of the charge is 1, so that's why in place of one of the charge, we are placing 1. So that's why 1 by 4 by epsilon naught, Q by R square. So, Q by 4 pi epsilon r is your D. As earlier we have discussed that it is the electric displacement vector. So, D by epsilon naught. Or if you cross multiply this, D is equal to epsilon naught E. So, this is the relation between the electric field intensity or electric field vector to the displacement vector D. This is a very important question, which is an important relation for problem. This we can use for problematic, for solving the problems in dielectrics. So relation between the displacement vector D and electric field intensity E. They are related by D is equal to epsilon naught E. Next, polarization. This is a very important phenomena because we are classifying the insulators to the dielectrics on the basis of polarization. What is this polarization? The polarization is the process of producing electric dipoles out of neutral atoms or molecules is known as polarization. Okay, so polarization means formation of dipoles. We know that. What is a dipole? Two equal and opposite charges, they are separated by small distance. Certain insulators, they exhibit this polarization. Not all the insulators they exhibit. Certain insulators, when we apply the high electric field, they exhibit this polarization. Those insulators, they are known as dielectrics. Okay, so that's why what is the basic definition of this polarization? The process of producing electric dipoles out of neutral atoms. Okay, we know that neutral atom means the number of number of positive charges is equal to the number of negative charges. That's why it's a neutral atom. Okay, so if to that neutral atom, when we apply the electric field, then what will happen? The positive and negative charges, they will separate. When they will separate from the nucleus, when they will separate from the nucleus, they form a dipole. So that process is known as polarization. So again, we are discussing, again, let's go to this topic, the process of producing electric dipoles out of neutral atom, or simply we can say polarization is nothing but the formation of dipoles inside the insulating materials. So that is known as polarization. The total dipole moment per unit volume is also defined as the dielectric polarization. This is the induced charge per unit area. Why it is induced charge? What is the difference between a charge and induced charge? Because induced means it is not initially there is a charge. That means they are separating. The charges are separating from the neutral atom. That's why it is a induced charge per unit area. Next, polarization vector. So the symbol is P. It is defined as the dipole moment per unit volume, and it is given by P is equal to mu by V, because dipole moment is your mu and V is the volume. Okay. So this is a very important question, which is important formula. P is equal to mu by V, which is known as polarization vector. So here we are getting three important dielectric vectors. So number one is your electric field intensity E, and the second one is a displacement vector D, and the polarization vector P. So these three are the dielectric vectors. If the number of molecules per unit volume is n, and mu is the dipole moment of each molecule, then P is equal to n. N is the number of molecules, n into mu. But the magnitude of polarization is directly proportional to the intensity of electric field. We know that when we apply more electric field, then more dipole moment will be there. So that's why P proportional to E. So P is proportional to polarization vector is proportional to electric field intensity, or simply electric field. So since they are directly proportional, in order to make the equal, we should keep a constant. So that is your chi and epsilon naught, or P by epsilon naught E is equal to chi. So where chi is the dielectric susceptibility of the material, which is characterized the case with the dielectric materials and can be influenced by external field. You should remember this equation. P is equal to chi epsilon naught E, where chi is the dielectric susceptibility. Next, what is a Gauss law? Gauss law states that the total electric flux through any closed surface is equal to the 1 by epsilon naught times the net charges enclosed by the surface. That is here you can see the equation. E integral ds is equal to q by epsilon naught. So this is the relation between how we can derive the relation between dep, and the relation is d is equal to epsilon naught e plus p. Next, types of polarization. So there are four types of polarization. First one, electronic polarization. Second one, ionic polarization. Third one, orientation polarization. And the fourth one, space charge polarization. Once again, four different types of polarization are there. So first one is electronic polarization. Second one, ionic polarization. Third one, orientation polarization. Fourth one, space charge polarization. So in the diagram, we can see. So this is the first one. This is electronic polarization. Electronic polarization is by the atomic, that is inside the atom, this electronic polarization occurs. Ionic polarization, it is applicable only for ionic materials, that is ionic solids, NaCl, KCl, like this. Orientation, so what is the meaning of orientation? Orientation means alignment of what? Alignment of polar molecules. So next is space charge polarization. The space charge polarization very small, which we can neglect it. But we have to go through this topic. All over, we are getting 4 different types of polarization. The first one, electronic polarization. It occurs due to the displacement of the center of negatively charged electron cloud related to the positive nucleus of an atom by electric field. That means we know that inside the atom, there will be positive and negative charges. So it occurs by when we apply the electric field, then what will happen? Positive and negative charges, they will be separated from the nucleus. So by the application of electric field, this kind of displacement will produce an electric dipole. When they far apart from each other, then they form the electric dipole with the atom. So this polarization is known as electronic polarization. So you should remember this. So electronic polarization occurs inside the atoms. The developed dipole moment is proportional to the magnitude of the field strength and mu E. Mu E is E for electronic polarization. So mu E is proportional to E. E is your electric field intensity. So since there is a proportionality symbol, so mu E is equal to alpha E E. In order to make equal, since they are proportional, in order to make the equality symbol, we are placing one constant. So that is your alpha E, and alpha E is called your electronic polarizability constant. So monoatomic gases such as the helium, neon, argon, krypton, xenon, they exhibit this electronic polarization. So you should remember this monoatomic gases, that is inert gases, helium, neon, argon, krypton, xenon, they exhibit electronic polarization. The order of this electronic polarizability, it is of 10 to the power minus 40 Fermi per meter square. It occurs only at optical frequency, that is at 10 to the power 15 Hertz. It is independent of temperature. That means if you increase or decrease the temperature, there will be no effect on the electric polarization. So this is the diagram of electronic polarizability. This is the neutral atom. So this is the nucleus, and now this is the electronic charge. Outside these dots are there. These are the electronic charges. So when we apply the electric field, what will happen? This positive charge, the nucleus is positive charge, and the whole negative charge is concentrated at a particular point. That is known as your sphere, that is sphere of electronic charge, and they will be separated by some distance. So that means if the positive charge will move in the direction of the field, then the sphere of electronic charge, they will move apart from that. So that is your electronic polarizability. So expression for electronic polarizability. So we are going to derive the expression. So let us assume that an atom of nucleus charge Ze is surrounded by electron cloud. So you know that what is the electron cloud? A group of electrons, they form an electron cloud. Okay, there's nothing confusion inside this electron cloud. Electron cloud is nothing but the group of electrons, they form a sphere, which is known as electron cloud of charge minus Ze and distributed in a sphere of radius r. Thus, the charge density is given by rho is equal to Ze by minus Ze by 4/3 pi r cube. So minus 3 by 4. Here the numerator is in the numerator we are getting 4 by 3. When it will go to the upward direction, it will be 3 by 4 Ze pi r cube. When the system is subjected to an external field of intensity E, the nucleus and the electron cloud experience a Lorentz force of magnitude Ze. Lorentz force means external force. Ze, Q, because the expression for Lorentz force is your QE. In place of Q, we are writing Ze. Okay, so Z is your atomic number, E is the electronic charge. So it will be in opposite direction. Hence, the nucleus and electron cloud are pulled apart. They will be apart from each other. If the nucleus, it will move in the direction of the field, then due to Lorentz force, the ZE will move opposite to the direction of the nucleus. A Coulombic force of attraction develops between them, which tends to oppose the displacement of charges. That means if the positive and negative charges, if they are separated by a distance x, then the expression is FL is equal to minus ZE. Coulombic force of attraction, FC is equal to, we know that Q1, Q2 by 4 pi epsilon naught R square. So, ZD into charge enclosed in the sphere of radius x by 4 pi epsilon naught x square. So, charge enclosed in the sphere of radius x is minus 43 pi x cube rho. So, Coulombic force is equal to ZD into charge enclosed in the sphere of radius x by 4 pi epsilon naught x square. So, that is your minus x is equal to minus 4/3 pi x cube. Substituting equation 1 in equation 4, we are getting this. And the Coulombic force Fc is equal to, this is the expression, minus z square e square x by 4 pi epsilon naught r cube. In equilibrium position, the two forces are equal. That is a Lorentz force and a Coulombic force. So the Lorentz force is minus ZDE and the Coulombic force is, we have derived this equation, minus Z squared E square X by 4 pi epsilon naught R cube. So E is equal to ZDX by 4 pi epsilon naught R cube. So X is equal to 4 pi epsilon naught R cube by ZDE. The induced dipole moment due to intensity of electric field is given by, so mu E is equal to ZD E X, and when we substitute this equation, if you substitute this X value in this equation, we will get this equation, and so mu is equal to, these all terms are, this 4 pi epsilon naught is known as alpha E. So this is your electronic polarizability, and here you are getting E. So mu E is equal to alpha E T. Thus, electronic polarizability is given by alpha E is equal to 4 pi epsilon naught R cube. Next, ionic polarization. This ionic polarization occurs in ionic solids. That is, we know that ionic solids, sodium chloride, potassium bromide. So where ionic bond exists. So how the ionic bonds occur? That is, a complete transformation of electrons. In covalent bond, we know that the mutual sharing of electron. But in case of ionic bond, the complete sharing of electron. If you consider sodium chloride, sodium has +1 and chlorine has -7. Okay, it has to, that is 7. So the sodium, it completely donates its electron. So this type of bond, that is complete transformation of electron. So the bond formed by this process is known as ionic bond, and this ionic polarization occurs in ionic solids. The example of ionic solids are, as we know that, sodium chloride, potassium bromide, etc. So this occurs only when external field applied. So we should remember this, because when we don't apply electric field, there will be no polarization. But here we have to apply the electric field for ionic solids. So ions can be displaced in the infrared region and nearly at how much frequency they require. That is 10 to the power 13 Hertz. This much amount of frequency is needed for ionic polarization. And this is a very little bit slower process in comparison with electronic polarization. Electronic polarization, it can be easily done. But of course, the electronic polarization can occur, but it's little bit slower process. So let us go to the how we can derive the ionic polarization. So expression for ionic polarization. So when an electron, that means Na plus, if you consider NaCl, Na plus Cl minus, that means that there will be two ions will be there. So when electric field is applied to the ionic crystal, positive ions are displaced through a distance x1 and negative ions are displaced by the distance. That is, if two atoms are there, if this is Na and this is Cl, then sodium will move to the left side direction and Cl it will move to the right side direction. That means if you consider the displacement of sodium is x1 and the displacement of chlorine is x2, then the total displacement is x1 plus x2. So then the restoring force, because the equation for restoring force is F is equal to K into X. So where K is a restoring spring constant. So the equation Cl minus Na plus. So without field, when there is no field, there will be no displacement. When we apply the field, then the x1, x2, we get the distance. So F is equal to Fr omega square, that is equal to Ma, where M is the mass of the ion and R is the displacement of ion. So for positive ion, the restoring force is F is equal to K1 X1. K1 is for the spring constant for your sodium. That is for first ion. So that is a M X1 omega square. For negative ion, that is for chlorine ion, F is equal to K2 X2 M X2 omega square. So Lorentz force is equal to E into E. K, that is in equilibrium. We know that in equilibrium, the Lorentz force and this force should be in equal position, should be equal. So when we solve this, x1 is equal to E into E by K1 and x2 is E by K2. So the total displacement is x1 plus x2. When we substitute the value of x1 x2, we get this equation. For x1, we are getting the E by M omega square. For x2, E by M omega square. So this is the final equation, E into E by omega square, 1 by M plus 1 by small m plus 1 by capital M. Small m is the mass of one that is sodium, and capital M is the mass of the chlorine. So induced dipole moment, we know that mu is equal to alpha IE. So mu is equal to charge into displacement. So displacement we are getting here. Here, this is the equation for displacement. So charge is E. So when we substitute this, we are getting this equation. We will get this equation E square E by omega square by 1 by M plus 1 by, that is small m, 1 by capital M. From equation 1 and 2, this is equation 1, this is equation 2. When we equalize these two equations, we will get alpha I for ionic, and alpha is the ionic polarizability. Alpha I is equal to E square by omega square, 1 by small m by plus 1 by capital M. So the ionic polarization is equal to N. What is N? N is the number of ions present inside the ionic solid. How many number of ions are there? So that is N. So N into alpha IE. So if you remember this point, there is a note, ionic polarization is inversely proportional to the square of the angular frequency of the molecules. Next, orientation polarization. Orientation means changing the direction. Orientation means to a particular direction. It occurs in polar dielectric molecule. What do you mean by polar dielectrics? That means where the dipole moment exists. That means in case of, if you know that polar substance, water is a polar solvent, H2O. That means there should be some dipole moment existing. So those materials are known as polar dielectric materials. This polar dielectric material, this orientation polarization occurs in polar dielectric materials. Okay. So if you consider H2O, this is very easiest example, H2O. So because we know that it possesses the permanent dipole moment. When polar dielectric molecules they subject to electric field, dipoles tends to get orient in the direction of the applied field. That means before the application of the field, the molecules are randomly displaced. Each and every molecule, they have their own dipole moment. If there are 10 molecules, 10 dipoles are there, each and every molecule has their own dipole moment, but they are randomly oriented. But when we apply the electric field, all the dipoles, they will orient, they will align in the direction of the field, which is known as orientation polarization. And the electric dipole moment due to orientation is alpha O, O for orientation. So alpha naught is mu is equal to alpha naught E. Alpha naught is equal to mu square by 3 kBt. You should remember this equation. Mu naught square by 3 kBt. This polarization is temperature dependent. That means if you increase the temperature, it is inversely proportional. And we are getting this equation. Okay. So when we increase the temperature, the orientation will decrease. So the polarization is dependent on temperature. With increase in temperature, orientation polarization decrease. This is very important statement. Okay. The polarization occurs below microwave region. And that is the microwave region is, we know that 10 to the power 6 hertz to 10 to the power 9 hertz. And the expression for orientation polarization is mu naught is equal to n mu naught n into and mu naught. Here we are getting this equation alpha naught E. And this is the diagram. Here you can see that the molecules, they are randomly oriented. When we apply the field, all they will align in the direction of the field. So the last one is your space charge polarization. So space charge polarization, it is occur due to accumulation of the charges at the electrodes. This is a positive electrode, this is a negative electrode. Some charges, they will be accumulated. If it is a positive electrode, so negative charges, some very small charges will be accumulated here. If the negative, if the positive, then negative charges will be accumulated here. So this type of polarization is known as your space charge polarization. This is the space charge polarization is very small. The total, because we can neglect the space charge polarization, and the total polarization alpha is equal to alpha E plus alpha E plus alpha naught. Alpha E electronic polarization, alpha E ionic polarization, alpha O orientation polarization. So when we add all this polarization, we'll get the final equation. And this is the final equation. Total polarization P is equal to Ne into 4 pi RQ. This is electronic, this is ionic, this is orientation polarization. And this equation is known as Langevin-Device equation. So this equation, you have to remember this. This is a combination of three different types of polarization: electronic, ionic, and orientation polarization. Thank you very much.